everyone. Welcome to today's Science Talk. My name is Dr. Miriam Axel, and I'm delighted to be your host today. For those of you who are joining us for the first time, we welcome you, and we'd like to let you know that all of our talks, both from the 2024 series with the amazing Professor Grace Oluwasanya and the 2025 recordings are available on our website at www.unu.edu/INWEH/science-talks with an S. Today's talk, like all the others, will be recorded, and the recording will be put up on our YouTube channel. Also, we'll conclude with an interactive Q&A session at the end, so we invite you to please put your questions in the Q&A, and I will read them out for our speaker. And you can put your questions in at any point. Don't wait until the end. And now the topic of today's talk is permafrost, carbon circularity, a bio-cementation solution for mitigating climate change in the Arctic. And I'm particularly excited to introduce today's speaker. We just celebrated International Women's Day on March 8th, and she's a fantastic researcher and professor, Professor Pooneh Maghoul. She's the lead for sustainable infrastructure in cold regions at UNU-INWEH. Professor Maghoul's research focuses on the intersection of geotechnical engineering and sustainable development by addressing the challenges posed by climate change in cold and permafrost regions. At UNU-INWEH, she leads initiatives on sustainable infrastructure in cold regions, covering a wide range of topics such as infrastructure resilience, circular economy, smart cities, digital twins, responsible extraction, aging infrastructure, and inclusive decision-making. She collaborates with communities in cold, permafrost, and northern regions to develop community-based policy frameworks that address specific vulnerabilities in cold regions to ensure that local voices are heard in the policymaking process. Professor Maghoul has been at the forefront of developing cutting-edge solutions and technologies to address critical challenges related to the resilience and sustainability of civil and mining infrastructure in the face of climate and disaster risks. Her knowledge mobilization and technology transfer contributions include pioneering the use of digital twin technology for smart infrastructure asset management, evaluating sustainable and low-carbon materials, and implementing nature-based solutions to mitigate permafrost carbon feedback. She's a professor of geotechnical engineering at Polytechnique Montréal and a recipient of several international and national awards, including the Outstanding Young Geotechnical Engineer Award from the International Society for Soil Mechanics and Geotechnical Engineering. Her work on enhancing the understanding of infrastructure resilience under the pressures of climate change has received recognition and funding from major institutions, including the Natural Sciences and Engineering Research Council of Canada and the Canadian Space Agency. And now, without further ado, I'm delighted to turn it over to you.
Thank you very much. It's a true pleasure to be here. Let me share my screen. Is it okay?
Yes.
Okay, awesome. Thank you very much. Hi, everyone. My name is Pooneh. I'm lead in sustainable infrastructure in cold regions at UNU-INWEH, and I'm also a professor at Polytechnique Montreal. Then this is the topic of my talk today, permafrost, carbon, circularity. And we will discuss a little bit, about the context, northern regions, what are the problems, and specifically at the end of my presentation, I will talk about our ongoing research on bio-cementation solution for mitigating climate change in the Arctic, or it would be better to say in northern regions. Then before I start, I would like to recognize the indigenous territory on which Polytechnique Montreal is located. I am based in Montreal, and the University of Montreal and Polytechnique Montreal is located where long before the establishment of the French, various indigenous peoples interacted with one another, and we wish to pay tribute to these indigenous peoples. Then I have three parts in my talk today. The first part is related to climate change in northern regions, and I will only discuss some consequences. of the impact of climate change. Then when we say the Arctic or northern regions, the first thing that we think is the ice, right? The other term that we use in geotechnical engineering, in ground engineering, is actually permafrost. And again, when we say permafrost, everyone thinks about those frozen soils, which is somewhat true. But if we want to define it precisely, it's defined as any ground that remains at or below 0 degree for at least 2 consecutive years. Then you can see in that definition that permafrost only deals with the thermal state of the ground. It has nothing to do with water, with ice, but it's a definition of the thermal state of the ground. And the problem in the northern regions is that groundwater is actually almost at the surface. Then automatically soil is saturated. When I say saturated, I mean those pores, within the soil is filled with water. Then when the temperature is below 0 degree, automatically we have pore ice. Then that's why when we think about permafrost and northern regions, we always think about, those frozen soils. But again, I repeat and I emphasize that permafrost is only about the thermal state of the ground. Then the top layer of permafrost, as you can see, we call it the active layer, which undergoes seasonal freeze-thaw cycles. And all the problems we have is actually related to the active layer, from geoengineering, from geotechnical engineering, from flood management, flood risks. Everything is related to what happens actually within the active layer. Then the problem with climate change is that the winter seasons, they are shorter. The warm season now, they are longer up north. And what's going on is that, the freezing thickness, it becomes more and more less than the thawing thickness. Then automatically over the year, we will have a kind of lake that we call it thaw lake, somewhere between the active layer and here that we call it ice or permafrost. I repeat, permafrost is defined as any ground. It can be 1 meter, 2 meters, 3 meters below the ground surface, and the temperature is between the temperature is at or below 0 degree for at least 2 consecutive years. Then the thickness of the active layer depends on many factors. For example, local and climate conditions, vegetation, snow covers, soil composition, air temperature, solar radiation, and wind speed. Then in here, you can see explicitly the impact of climate change, air temperature, solar radiation is somewhat, we can say the same, but wind speed, etc. And climate warming will lead to permafrost thaw. Then we should never say permafrost melting, it's permafrost thawing. Why? Because ice melts, but permafrost thaws because permafrost again is the thermal state of the ground, and increasing the thickness of the active layer in many different permafrost sites. Then in here you can see, actually it's from the IPCC fourth assessment report. It is old, back in 2007. I couldn't just find the new one from, the recent IPCC reports. But here you can see even in 2007, based on the data from 2004, you can see in different areas, Alaska, Russia, Canada, you can see this increase. Then now we are worse than that. Then Canada is going like this, like in other regions. Then the other thing here I want to show you is this, the concept of permafrost. Imagine that we go to the site, we do borehole and we bring like soil sample, permafrost samples to the lab at different sites, and we put it on the desk in our lab and we just watch them. 3 samples, they are permafrost soil samples. But you can see their behavior to warming or climate warming, their response is completely different. It's just, the message is that soil is a very complex, material, natural materials. If, for example, you have coarse grained soils, the way that it behaves is completely different from if you have like ice-rich permafrost. And for each, we have actually specific definition. Then when we deal with like silty soil, fine-grained soil, they become automatically ice-rich. Why? Because the pore size is too small, and it like, they soak up the groundwater to the surface. The temperature is below degrees. Then it change the state from liquid to solid state. And what happens is that automatically we have the creation of these ice lances. Let's say for one portion of soil particles, we have like 10 portions of water ice. Then when it thaws, automatically you can see that we have like 10 portion of water for just a very little amount of solid particles in here. Then now imagine you have building, highway, runways sitting on top of this. Then if you want to visualize what I mean, just wait. In a few minutes, I will show you the consequences of that. Again, to tell you that geopolitically speaking, these northern regions are very important for all these countries. Specifically in Canada, if I want to show you here, UNU-INWEH is placed somewhere in here. I am now in Montreal. I think I am somewhere in here. Then we are in the southern part of the country. But if you look at this map, you can see that over 50% of Canada's territory deals with this problem. Permafrost regions, northern regions. And when we go up, 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 it becomes the Arctic regions. Then we have also about 280 active remote communities up there. And 239 of them heavily depend on diesel fuel for electricity generation and oil for heating. And the good message is that these regions are very rich in minerals, natural resources, potential for economic development. Then, but the issues for now with these communities is that in many parts we use winter roads. And winter roads is that by definition, status quo, the ground is all the time over the year, it's frozen, lakes are frozen. Then it's really easy to ship goods up north through these, routes. But the problem with climate change is that now we have like 3-4 months of frozen lake. Then these communities can communicate and do commerce with other regions of the country just for 3 months, while 20 years ago, 30 years ago, it was like 10 months. This is the difference. They are highly dependent, on all the resources we send north from the southern part of the countries. And if you look at Nunavik, which is the northern part of Quebec, there's also no roads. The only way to communicate with do commerce with these communities is through airports. Then I just took some the articles just to show you a little bit about the problems we have. This one is December 2024, and you can see the title of the article, Thawing Permafrost Threatens Runways in the North. This was from a report from the Canadian Senate. Then if you look at this, you can read it, some part of the article, that thawing permafrost poses a threat to northern runways. And most northern airports have gravel runways that were built on permafrost during the Cold War and have received few upgrades since then. And the thawing permafrost destabilizes runways, which compromises the safety of northern aviations. The other one is again from September 2024 from CBC, and it was written work plan for Yellowknife Airport to deal with thawing permafrost. Then more and more we see actually this term thawing permafrost or degrading permafrost. And it just, the message is the thickness of the active layer, as I told you. It's not only the problem in Canada. All the other, these northern countries deal with the same problem at different, the scale. I took this one from, the Russian news in English, of course. And you can see again the same thing. Permafrost thaw threatens Russia's ambitions. Then what is that ambition? Is that according to the European Space Agency, climate change could result in an Arctic sea free from summer ice by 2050. It is good or bad, it depends. Of course, it is bad, but from the economic development, doing commerce between the countries, it can be actually an opportunity. And someone told me, I don't know the reference for this claim, but someone important from the government told me once that if we can actually do commerce through the Arctic regions, we can reduce, the travel time by 80%. Then you can see again from the carbon footprint of this, all these consequences of um, doing international trade. Then the message is that it allows longer shipping seasons along the northern sea routes and the transpolar sea routes. It is good, but the message is that if we want to do commerce through these, the routes, we have to ship through our roads, transportation system, roads to these regions, and then ship it to other parts of the world. And Russia, like Canada, they deal with exactly the same problems. Then it's also important to mention the geopolitical impacts of that. When we say permafrost and ice, it's not the same thing. I told you, from that 55 degrees up north, we deal with these northern regions, frozen ground because of the presence of underground water table. And if you look at this map, we can see we have different types of permafrost. For example, we have this continuous, which is up north in the Arctic regions. Then we have extensive discontinuous, sporadic discontinuous, isolated, and subsea. Then look at just this discontinuous. It's like ice patches, sporadic, isolated, again, like these small ice patches. And imagine if you want to build a road or if you want to build a pipeline from the southern part of the country to up north. Then for what type of ground you want to build, then just reduce, the scale. Those who are in science, they really work on regional, scale. But in ground engineering, in civil engineering, when we build a structure, we are at engineering scale. Then if I, for example, as an engineer, I do recommendation or, do design work for this part of the infrastructure, it would not be the same thing as, for example, this part. Why? Because in 2025, I still have ice patches, but it will change. In 10 years, 20 years, 15 years, the ground will not be the same. Then for what type of, the ground, for what conditions I should design, what type of mitigation or adaptation measures I should consider, in my design. And this is actually what you can see here. It's all these airports in Nunavik up north in Quebec. And this actually shows the differences we have, at the ground surface temperature. Ground surface temperature is not the same thing as the air temperature. It's different because of, the vegetation, snow cover, and all other factors we have. And if I want to show you here, you can see here we are in this shows the average, the mean annual ground surface temperature anomaly, and different villages we have, communities we have in Nunavik. And this is 2025 today. And here you can see, just look at this, it's until 2100. The message is we are still fine. The impact will start sometime in 2030, you can see 33, when it becomes yellow, orange, and red. Then if today we have this problem, just imagine in 10 years, what would be the consequences of climate change? And Mother Nature doesn't wait for us. It goes faster than us. But in terms of adaptation and technology development, sustainable development, where we are, I have no comment on that. Again, that map that I showed you, it's related to ground surface temperature. It's not the only factor we should consider in the engineering design. We also have precipitation anomalies, we have wind speed anomalies, and other, the important aspects that we should consider in our engineering design. It doesn't mean that we do not do anything. We are active, we do lots of interesting work, but we all know that those mitigative measures will not necessarily work in 10 years, in 15 years. And more, we need actually innovation, invention, to deal with uncertainties we have in the future. Then the consequences of ice melt or permafrost thaw is that ice becomes like liquid, then permafrost degrade, soil lost its strength, and we have excessive ground surface deformations, we have infrastructure failure, etc. And it's not the only thing. I am more actually worried about the other aspect of climate change. And what we know today is that the high latitude areas are known as a significant potent components in which a large amount of carbon is stored. These images you can see, this is related to ground deformation, about permafrost thaw, that strength loss, everything. But what you can see in this animation is just in terms of carbon. And today we know that permafrost is likely the greatest source of terrestrial carbon sink in human history. And what we know again is that it's currently estimated that permafrost stores about 1,500 billion tons of organic carbon, which is distributed only in a shallow depths of 0 to 3 meters. Then when permafrost or soil is frozen, it is good because it behaves like a solid materials. The pores are filled with, the ice. There is no room for gas, the transfer and carbon emissions. But with that active layer thickening and permafrost degradation, we actually open the door for these greenhouse gas emissions to the atmosphere. And what we know, that amount of carbon which is today stored in permafrost is about twofold the amount of carbon we have in the atmosphere today. And the bad news is that we have not taken this into consideration in all those IPCC reports, as far as I know. The recent ones, we started talking about this, but today all the climate models, we have not considered it yet. And what we know that emissions from permafrost are already estimated between 0.3 to 0.6 billion tons, which is equivalent to 7% of the world's total carbon emissions from burning coal, oil, and natural gas. Then it's really important to think about it and see how we can actually mitigate it. And think about the large scale, 40%, 50% of Canada's, the land is covered by this issue. Then this is the carbon map of Canada. Again, those bluish things it shows the sites which are very high in carbon. And why we have these phenomena, it's something we call it permafrost carbon feedback loop, that permafrost thaws, microbial communities wake up from a frozen slumber and begin to metabolize the carbon that's stored in the soil, and it's released to the atmosphere. Then we have this loop that we release greenhouse gas, to the atmosphere. We warm further, we accelerate climate change, and due to those, climate warming, we have more and more permafrost thaw, and again, we have those carbon emissions. And cumulative permafrost emissions could reach 150 billion tons of carbon by the year 2100 without aggressive climate policies or climate change adaptation strategies. Yeah, these are just a general context of what we know about the northern regions. And when I say about that permafrost carbon feedback loop and carbon stores, the issue is that it will not just warm up Canada. I mean, all those countries that deal with like coastal erosions, even the global south, we will pay for the consequences of, again, this climate change. That's why it's really important that we think about different ways to mitigate it. We can never stop it, but how we can actually deal with this problem and reduce it. One of them can be the afforestation, but again, with all the risk related to wildfire, is it really helpful? We do not know. Then the second part of my talk is related to sustainability, climate technology adoption, and how we define sustainability in ground engineering. It's again, the definition is the long-term performance, durability of structures, promoting the efficient use of resources, minimizing environmental impact. The carbon footprint, it becomes more and more important. And why I'm saying that, because in ground engineering, they are still new concepts. When we want to build a residential building, a road, 10 years ago, when I was actually in industry and working on different engineering projects, it was not really an important topic. It was not even considered, in the engineering, from engineering actually viewpoint. But more and more it becomes important, and we have to think about the different ways to reduce, the carbon footprint in a construction project. The production of materials, transportation, construction itself, operation, maintenance, end of life deconstruction of the structures becomes more and more important. For example, if we want to rehabilitate in a project, or we want to destroy a building and rebuild it, how we can deal with the piles in the soil. All of these things related to this end of life deconstruction of the structures, and how we can reuse them in new engineering projects. And today, construction and built environment accounts for about 40% of global greenhouse gas emissions. And again, how we can consider these things in the engineering design. Then in geotechnical engineering, ground engineering, again, you see many things. For example, how we can manage waste, construction waste, infrastructure development and rehabilitation, construction efficiency, smart building. There are different things, but again, are we using all of these concepts in an engineering project? Not everywhere. And what is actually the readability of these new concepts? In my opinion, very low. I took this from LinkedIn. I think it was like last year. It was after COP 28. And the message was, to reach the 1.5-degree target, we need to transform our economy at the scale of the Industrial Revolution, but at the speed of the digital revolution. And in order to do so, climate technology is key. Again, just think about 40% of global warming is related to construction, ground engineering. Ground engineering is part of that construction. It's not the only thing, but 40% is huge. And now the big question in my own field is that climate technology, we should develop it at the speed of the digital revolution. But how? And what I want to talk later, it's actually deal with this problem. And again, sustainability technology. Technology itself is very good. It's nice. You can see today with all of these AI, revolution, everything, and we should use AI in everything. But we should be cautious because there are in some fields, like when we touch materials like ground engineering, we cannot revolutionize the stuff at the speed of AI. And why? Because if you work on technology development, if you have ever had the opportunity to go to those incubators and pitch your technology, the first question they ask you is, what is your TRL, or technology readiness level? And what is TRL by definition? You see that this is the concept from 1 to 9. And during the Apollo missions, back in 1960s, it was a concept developed at NASA. And they wanted to use, if, for example, I'm here, I'm talking to you, brainstorming with you, and I want to develop basic principles of concept that we observed and we report. And how long it will take to use it in the market at a larger scale. Then you see that from 1 to 9, so many things happen. And when in the lab, we develop a drug, we develop like sustainable technology, those carbon capture stuff, or I want to do something like green cement. I do lots of interesting things in my university lab. I reach TRL 4, 5. My students graduate, and how I can bring this new technology to the market at the larger scale that everyone can use it. Then if today we use those Portland cements and traditional concrete, there is a message. We do our best to develop new materials. But the problem is that we are still at 4, 5, 6. It's really hard to reach TRL 9. And why in construction it's important? Because it's not just about the technology. It's not all about like AI. We have no regulations right now related to AI, and we are fine with that. ChatGPT didn't need to get any permits for the technology, AI technology. But when we are in the construction and civil engineering, we have so many standards. I cannot just bring something to the market and say the stakeholders use it, but ASCE has nothing related to that in the standards and codes. Then I can never use it. This is the bad message about, all this sustainable technology in the construction field. Then what I want to present you later today is just to tell you we are at TRL 4. Then don't ask me, please, if we've used it in the field or in industry, not yet. We are working on that, and we aim actually to reach like TRL 8, 9, and everyone can use it. Then problematic soils and SUSTEC, sustainable technologies. I already showed you these images related to permafrost. It's not the only thing. In cold regions, in even other harsh environment, like, I don't know, those who deal with extreme heat, we have such things too. Just the context is different, the soil composition is different. Coastal regions, many parts of the world, we have also what we call it retrogressive thaw slump up north, which is like glissement terrain. We call it in French, landslide, sorry. And you see that they are all related to not only climate change and environment, but also soil type we have. For each soil type, we need to develop new things. If I, for example, develop a new technology for ground improvement, for soil improvement, for sandy soils, it doesn't mean I can use it even in clay. Then we should be really cautious about that. And we have liquefaction, all of these things, failures with fatality, unfortunately. You can see these are related to problematic soils. How we stabilize soil for all of these, things that I showed you. We go to, as an engineer, we go to the site, construction site, we do some tests, we do like drilling, we extract soil samples, we bring it to the lab, we do some tests, we analyze, and we see what is soil strength and how we can do engineering on top of that. If the soil is not good, if the site itself is problematic, this is the way that we try to stabilize soil. Um, we do like dynamic. I'm sure that you've already heard the dum 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 in the construction sites. It's actually what we call it SPT. It's not for dynamic things, but through those hammering, we try to more the stabilize soil, compress soil. And the other things we use is like, imagine chemical stabilization, cement and lime, and we mix it with the soil, and it's like dirty everywhere, but it's the way that we treat soil purely from engineering perspective. And it's really important to mention it, from the indigenous perspective. They, for them, land, soil is like their mother. They respect it. But the way we do engineering, purely engineering, we don't care about, other things, environmental impact, all of these, beliefs. It's the way that we do like soil stabilization. I cannot go as a geotechnical engineer to a community and say, I want to stabilize your soil because your foundation is like this, then let's mix it with cement. And that's why we actually need, with the consequences of all those ESG, um, environmental, social governance perspectives, how we can make it like responsible engineering work in a construction site. There are new concepts, and we have to just change the way we do things. One of them is how we can, for example, use everything we have available, recycle, for example, agricultural waste, and even take advantage of soil itself. Soil is a living material. We have lots of different things, microbes in it, fungi in it. How we can actually stimulate this living stuff within the soil and use it for calcification and for improving soil strength. This is actually the concept we are working on in my lab. Different things. MICP is how we can stimulate microbes, in situ microbes in the soil. We do engineering and we actually calcify things. Then, like if you have a mud, your mud becomes like a rock. And this is the consequences of calcification within the soil. Then MICP is microbially induced, calcite precipitation. The other one is enzyme induced, is that we do not go to the site and stimulate directly the microbes, in situ microbes, but I use like plant enzyme, like beans. And I prepare my solution in the lab, and I go to the site and inject those liquidish solution to the soil and try to calcify it. Then I can increase the strength of the soil. But the other technique we can use is like fungi-induced carbon precipitation. Use those fungi, mushrooms in the soil, and stimulate them, engineering them, then they will take care of soil itself, muddy soil, weak soil, and try to calcify and improve, the soil strength. Then these are the different techniques we do in the lab on different soil types, as I told you. Tailings or mine wastes, crushed rocks, It becomes like fine-grained soils. We have clay, we have till, which is a mix of everything you can imagine. We also have permafrost soils, we have peat, degraded materials, etc. Then this is actually the different techniques we do in the lab. And again, just from that TRL, technology readiness level perspective, it doesn't mean that for now it works in the field, in the real construction site, but these are the steps we have to do. The first example I'm going to show you is related to nano-enhanced MICP for clay stabilization. And we use that microbially induced carbon precipitation. We stimulate in situ microbes, but in order to make it, for clay, we have to add other additives. One of things that we do in the lab is how to use nanoparticles to just make it better. Then we do like macro scale tests, soil samples. I will show you. We do some geotechnical tests in the lab, uniaxial tests, triaxial tests, large scale tests just to see if we scale up a little bit from that 10 centimeter soil samples. We do like a slope, 1 meter slope in the lab. We put it on a shaking table test or centrifuge test to see how it behaves at a larger scale. And at the same time, we did some micro scale testing through microscope, X-ray diffraction analysis, chemical analysis to make sure that what we've observed at the soil scale and large scale test from the pore scale, we observe the same thing. And once it's done, we go to the field, to the real construction site. We do some boreholes, we inject our solution, and we wait. 1 year, 2 years, 3 years, just to see if the solution works or not. Then think about that. We should develop technologies at the digital, speed, and things take time. This is actually the bad message, and nature does not wait for us. But this is the way we work in ground engineering. We have to wait and see how our solution actually works after 5 years, 10 years. Is it really reliable or not? And if it works, then we go and knock at the ASCE door and say, can you please develop a standard for our technology? Then these are actually, you can see here the way that we prepared samples. These are the small soil samples we developed in the lab. We put it, on the pressure just to see how it behaves in comparison to untreated soils. These are actually, you can see some results here. That red line shows untreated samples. And when we treat it with those MICP concept, mix it with nano particles, you can see how we can improve soil strength as I repeat, at the soil sample scale. These are some, the results at the macro scale. We put very tiny part of the soil sample under the microscope, and we observed at the pore scale what's going on, and we could observe actually the presence of this calcium carbonate, calcification I told you. Then we made this a slope. You can see here the inclusion, these columns. We injected our solution in the soil. We waited for the calcification process. We did centrifuge test. The way it works is that the message is that you want to actually see how this solution, this sustainable technology works. For example, if we want to use it in a dam, or in a slope, in an embankment, then we cannot in the lab build like 1 kilometer's length dam. It will never work. Then mg, mass times g. Then we reduce the mass of that 1 kilometer dam, but we increase g. That's why we have this centrifuge concept. And we hope that the things that we observed in the lab through the centrifuge test, it shows that at a larger scale, 1 kilometer scale, it will work the same way. Then we did this centrifuge test up to like 70 G. It means that my 1 meter slope that I built in the lab, it represents kind of 11 meter slope. by increasing G. These are the results of unimproved ground without any inclusions. You can see these, the black lines is we put it intentionally in the soil layers, and the red lines here shows the inclusions we had, and you can see the presence of these failures mechanism. This is not the same thing. Look at these black lines. Then we tested on our improved ground with the with solution inclusion. As you can see, we increased, I told you 70, but 77G, and you can see there is no change. And what does it mean? It means that if we treat soil the slope with those clean or SOS technology, at least at the centrifuge scale, you can see that it works. We also tested on tailings. And what are those tailings? I told you these are the mine waste that we put all these, the crushed rocks, silty soil layer by layer, and we build these tailings dams. And every year, recently, I think there was another failure, if I'm not mistaken, in Africa. And unfortunately, the consequences of these tailing dam failure is really, really bad for the communities living around these facilities. Then we tried to treat these tailing samples, different type of tailing samples, with another solution, this time EICP. And we actually, again, try to improve the performance by adding zeolite on that. And again, you see how we can improve the strength of our soil samples. These are, just look at the samples, these fibers we made through those, the solutions, clean solutions we injected into the soil. You can see the presence of these fibers that keep the grains together. And we did some, again, macroscopic analysis just to see at the pore scale the presence of this calcification and biofibers that we, made it in the lab. And also for permafrost soils, peat soils, ice-rich peat, we put it, you can see that this is, we thaw it in the lab, and you can see it becomes like a small scale lake. We have like very thin layer of soil particles and 3 portions of water due to this ice melting within the soil. And we injected our solutions. We put it in some capsules, as you can see. We injected in the soil, and it became like, for now, a like of cheese. We are still waiting to see, for example, after 30 days, after 2 months, how it behaves. But it's just the way that we try to deal with this living, the world. Soil is, the natural material with lots of microbes and organic matter, but how we can engineer, what we have already in the soil to improve the soil strength for construction purposes. The conclusions of my talk is that we can develop nature-based solutions. We can recycle all these, the agricultural waste, other type of waste, for ground improvement purposes. I put all of this in sustainable technology development, nature-based solutions for ground engineering. The big issues for now is that technology readiness level. We cannot use it at a larger scale. We cannot bring it to the market for now because of all the issues I told you. The other problem we have is how we can scale up these technologies. In the lab, it works well, TRL 4.5. But when you go and pitch it to an investor, the first question is that how we can scale up your technology and use it in any type of, soils. For example, if I use it in Montreal, can I use it in another part of the world, in, I don't know, in India, in Africa? Can I use the same solutions? And the answer sometimes is no. Then think about the concrete again. We can use it everywhere we wish. But with that, nature-based solutions, it doesn't mean that around the world we can use exactly the same solutions. And the sustainability. Sustainability from engineering viewpoint is not only related to technology itself, It's also about the economic aspect of a technology. And if we cannot justify it in a construction site, no one will use it. This is the bad message about the, sustainable technologies. Then here to acknowledge all those partners that actually supported this research, and also my PhD student, Sarah, who has been working hard to develop these concepts in the lab. Thank you very much.
Thank you so much. That was a really, really fascinating presentation. I especially liked all the pictures and the videos and images you had. It really makes it feel like you're in the field with you. So that was really great. We already have some questions in the chat. Dai Wang says, thank you, Professor Maghoul. Very nice presentation. What do you think is the greatest challenge for all-season road construction in the permafrost region in Canada? And can we transfer some knowledge from other regions or countries?
The big problems I see again, we call them linear infrastructure, thousands of kilometers. Soil will different. We all the time we say the impact of climate change, but these are external loads like precipitation, air temperature, climate warming. And I assure you, you can find some regions that climate change is really bad, but soil is good, then we can manage it. But you can find in some areas that the climate change itself, climate warming, or the precipitation patterns is mild, but the soil is problematic. Then you can have actually bad consequences. You need new technologies to improve the ground. Then we need to have kind of holistic approach. Through remote sensing, satellite imaging, it gives us actually very good tool to monitor infrastructure. And the other challenge I see is that those ground-based sensing system, we go and install like some sensors in the ground, but after 6 months, 1 year, they stop working because of, I don't know, an animal is there, or we have like huge precipitation in the region and the sensor stopped working. Then we do not have this like digital twin concept that we can in real time see and know about the health of infrastructure itself. It's not just about northern regions. We can see this in so many other remote areas in other parts of the world. Then yeah, conditions, climate change, lots of uncertainties, ground conditions, lots of uncertainties, and doing engineering, at a larger scale, it itself also is a challenge.
And then there's a question from in the room. Maybe I'll let you.
Thank you, Dr. Maghoul. Very, very interesting presentation. I was just wondering, my background is in epidemiology, and I read some years ago about an outbreak of anthrax that had killed like a 2,000 reindeer in Siberia, linked to like a 75-year-old release of anthrax from melting permafrost. And I was just wondering, if you could comment maybe a little bit on what degree of kind of collaboration with epidemiologists or microbiologists or public health professionals is taking place to kind of monitor, this potential revival of and release of new and emerging pathogens from permafrost.
Thank you very much. Super interesting talk. Sorry, not talk, question. I hope that you invite me another time, then I can present or research on exactly what you asked. This time my presentation was really related to those, nature-based solution for ground improvement. But I also work on another thing on the impact of microbial activities on everything that you ask, on permafrost carbon, this interaction between microbial communities and and nutritions, those vegetations, afforestation and all of these, because these are the contributors of, climate change. And if you let me, I want to just share something with you, just to give you the, can you see it? Can you see
Yes.
my screen? What we try to do, at a larger scale now, it's a trend. There are different scientists who work on that. They monitor different sites, methane emission, carbon emission in different permafrost regions. You're totally right. The strange microbes that we can actually observe, that after millions of years they become active. Then what we try to do in the lab, we develop a kind of microfluidic microchips platform, exactly the same way that those who are in drug, industry, the way that they work. We develop a kind of microfluidics platform. We work with actually some colleagues at the University of Alberta, and they informed us about the different microbes they identified in permafrost, sites in Mackenzie Valley. Then what we try to do is we prepare our microbial solutions, we inject it into microfluidic, we put some sugar, a kind of nutrition for microbes, and we monitor actually the way they behave. And we are building a chamber in the lab, and just to see how the concentration of carbon changes, just to be able to monitor that. I'm not an epidemiologist, as you said. I don't know the consequences we may have actually with the health issues, but from carbon emissions perspective, it's actually the way that we try to deal with it, just because there's no knowledge on that. We do not know how these microbes behave. These are new things we actually observed in the site. And here again, you can see how we try to see this movement of microbial communities within, this source of nutrients that we provided. Then maybe in a few months, I have better results to show you and answer better your questions.
Oh, that's great. We look forward to having you back.
Thank you.
You have another question in the chat. It says, great presentation, Professor Maghoul. How about the upscale of these natural solutions? Do you have a pilot scale experience? How was the results? Do the stakeholders get excited about the results? And if not, how far off are we for that?
I made a presentation a few months ago. I cannot mention the name of that company, but it's actually a big stakeholder in Canada. They reached out to us and they asked us if we can test our solution in a problematic site we have in Ontario, close to you. And we're working now with them just to see how we can. I cannot say and claim that we are scaling up our solutions. I told you it is really long, the process to go and test it in the lab and say everyone, this is our green, like concrete for ground improvement, and use it. We go step by step, baby steps. Then I hope that in a few months we will be able to test it in a real construction site. The site is really problematic. And yeah, now the next step to test it in the real condition, in a real field, and see if the technology works or not in real conditions.
And then you have more appreciation in the chat. We really appreciate your time, and a question about how to access the file presentation. So I will share the papers that you shared as well. The recording will be made available on YouTube. And I think we're almost out of time, but with that, I'll pass it over to our director to close.
Oh, yeah, just because we are over time, but thank you so much, Pooneh. I just wanted to endorse the point that, so this issue of combination of matters that, like, so there is this global anthropogenic threats called climate change, but the impacts can be, very different depending on the location. And the issue of soil keeps being ignored, and the value and the importance of it, and the fact that these carbon sinks becoming carbon sources is a big deal. It's striking that not enough attention is being paid to this, because fixing this issue or mitigating this issue is much easier than, let's say, getting rid of fossil fuels or so some of those things that we're after, that to an extent are also politically motivated, but we are focused so much on those that we're distracted, and we miss these very, very important and strategic opportunities that can be very cost effective for us. So I hope your work highlights that further, and the policy briefs and reports you would be publishing would encourage the member states and other agencies to pay more attention to this. And I hope you can also promote your work through the UNCCD platforms. Thank you so much for this.
Thank you very much. My pleasure. I hope to see you soon. Thank you.
Thank you so much. Really wonderful presentation. We'll be sure to share out the papers that you provided and the recording shortly. And we look forward to seeing you back again soon for another presentation.
Sure. Thank you very much. Bye-bye.
Thank you. Bye.
Thank you.